Ladies, this is Chapter 3, Section 5, and we're looking at Example 3. I apologize that we didn't have time to touch on this in class the other day, so I want to do this screencast with you now because this problem could be a little bit confusing. It says the half-life of radium is 1,600 years. A, if 1 kilogram is present now, how much will be present after 3,200 years? And B, how much will be present after 4,000 years? Well, first off, this is going to be, we've got to determine what type of model to use, and this is exponential decay. And it's decaying because I have a half-life. So the life of the radium is decreasing. The model for exponential decay is the amount equals the initial amount times E to the RT power. R is the rate of decay and T is the time in years. Or you could also, instead of using R, remember we were also using K. All right, so let's first find our model so that I can determine example A and B. Half-life tells us that the amount will be half of the initial amount after a certain amount of time. Let me say that again. Half-life tells us that our amount will be half of the initial amount after a certain amount of time. Let me say that again. I wrote that incorrectly. Our amount is equal to half of the initial amount. So when we're filling in this model, I can replace A with 1/2 A sub 0 and then set that equal to A sub 0 times E to the R times T power. I immediately notice that my A sub 0's can cancel, and I now have half equals E raised to the RT power. Let's look back at the initial example. It says the half-life of radium is 1,600 years. So I know that my time in my model is equal to 1,600 years. So I have half equals E to the 1,600 times R power. And you may be using K. Remember, K is our rate also. Now I can solve this equation for R, and it will allow me to find the rate at which the radium is decaying. To solve for R, I have to take the natural log of both sides in order to get R out of the exponent. I know that the natural log of E to the 1,600R is 1,600R. And on the left, I have the natural log of 1/2. To continue to isolate R, I should divide both sides by 1,600. And so now I have my rate. And if you calculate this, you'll come up with negative 0.0004. Let's double check that. Okay, so I'm going to calculate the natural log of 1/2 and divide that by 1,600. And that does come out to be negative 0.0004. So that tells me my rate. Well, let's go back and use the model that we have now to determine the amount that will be present after 3,200 years. So we have our amount is equal to our initial amount times E to the negative 0.0004 power times time. If 1 kilogram is present now, how much will be present after 3,200 years? 1 kilogram would represent our initial amount. So A is equal to 1 kilogram times E to the negative 0.0004 power times 3,200 years. So our amount is equal to, let's see how many kilograms that gives us. E raised to the negative point, actually I'm just going to cut and paste. If I cut and paste this value here, it would be equivalent to putting in negative 0.004 times 3,200 years. And that tells me that I have 0.25 kilograms. I want you to see that if you type in, if you don't cut and paste the exact value for the rate and just type in negative 0.0004 times 3,200 years, your answer will not be quite as accurate. You'll have 0.278. So do cut and paste your rate in so you'll have a more accurate solution. So we know that that is 0.25 kilograms. And that's our amount after 3,200 years. So how could we determine after 4,000 years? The exact same way. A is equal to 1 kilogram times E to the negative 0.0004 power times 4,000. And let's see what we get there. Again, I'm going to cut and paste the exact rate, then multiply that exponent times 4,000, and we have 0.177 kilograms remaining. And so your amount should be decreasing. What was that again? 0.177, because it is decay. Ladies, this should help you with homework problem 25 and 27. Thank you. I hope it helps.